In this video we're going to prove a relationship between the dimension of the kernel of a linear map and the dimension of its image, which is called the rank-nullity theorem. To begin with, here are the definitions of rank and nullity. So if we begin with a linear map T from V to W, then the nullity simply means the dimension of the kernel of T, and the rank means the dimension of the image of T. To return to the examples of linear maps and their kernels and images which we saw in the last video, if we take A to be the matrix 0, 1, 0, 0, and we take TA to be the linear map from R squared to R squared defined by left multiplication by A, like this, then what we saw in that case was that the kernel of A, or the kernel of TA rather, was equal to the set of all things of the form, I'll write it slightly differently to before, x0 for x in R. In particular, this is a one-dimensional subspace of R squared, so the nullity of TA is 1. And the image in this case was actually the same as the kernel. So again, it has dimension 1, and the rank of TA is also equal to 1. And let's notice one interesting fact: 1 plus 1 equals 2. In that case, the dimension of the kernel of T, so the nullity, plus the dimension of the image of T, the rank, is equal to 2, and 2 was the dimension of the domain of our linear map TA. You'll see why I'm saying this in a moment. So let's return to the second example. We have D, which was a linear map from the space of all polynomials of degree at most n in the variable x over the real numbers, to the same vector space, defined by d of f is the derivative df by dx, and in that case the kernel of D was the set of all constant polynomials. So I'll write my constant polynomial just as a constant, like this. So in this case, this is spanned by the constant polynomial, which is equal to 1. So it has dimension 1, and the nullity of D is equal to 1. The image of D we showed was equal to the set of all polynomials of degree at most n minus 1. So that has dimension n, because the polynomials 1, x, x squared, up to x to the n minus 1 will form a basis. So the dimension is n, and therefore the rank of D, being the dimension of the image, is equal to n. So again, if we add the nullity and the rank, we get 1 plus n, and that is the dimension of the domain of our linear map D. Okay, in both cases, if you add up the rank and the nullity, the result is the dimension of the domain of the linear map. That is a general fact called the rank-nullity theorem, which we're now going to prove. Here's the statement of rank-nullity. It says for any linear map T from V to W, we have the rank of T plus the nullity of T is equal to the dimension of V. In other words, the dimension of the kernel of T plus the dimension of the image of T is equal to the dimension of the domain of T. We're now going to try a proof. So for our proof, we start off with noting that the kernel of T is a subspace of V. So we can take a basis for that subspace. So let's let K1 up to Kn be a basis of the kernel of T. This is a linearly independent set, or a linearly independent sequence rather, inside the vector space V. Any linearly independent sequence can be extended to a basis of V. So we're going to do that. So we'll call the extra vectors which we have to add in to get a basis of V, V1 up to Vm. What we're then going to prove is that the vectors T of V1 up to T of Vm are a basis of the image of T. Before we do that, let's see why that's enough to prove the theorem. Well, if that's true, the dimension of the image of T, that is the rank of T, is going to be equal to m, since we have a basis T of V1 up to T of Vm of size m. The dimension of the kernel of T, in other words the nullity of T, would be n, since we used n as our name for the size of the basis of kernel of T. And the dimension of V would be n plus m, because we used m as the number of extra vectors we had to add to k1 up to kn in order to get a basis of V, and the dimension of V is the size of a basis of V. So if we proved that claim, we would have proved the rank-nullity theorem, because we have the rank being m, the nullity being n, and the dimension of V being n plus m. Okay, so that's all we need to prove, that T of V1 up to T of Vm forms a basis of the image of T. To prove something is a basis, you have to prove that it is a spanning set and that it is linearly independent. So in our proof of the claim, let's start by showing that it's a spanning set for the image of T. To prove that T of V1 up to T of Vm spans the image of T, I have to show that every element of the image of T can be written as a linear combination of T of V1 up to T of Vm. So we'll pick any element of the image of T to begin with. Well, an element of the image of T looks like T applied to a vector in V. Well, V is an element of the vector space capital V, so we can write it as a linear combination of our basis of V. So we'll call the scalars involved in that linear combination ai's and bi's, and those ai's and bi's belong to the field over which v and w are vector spaces. So let's just call that bold F. Now let's see what happens to T of v. Well, T of v is T of this sum. But remember, T is a linear map. And linear maps respect scalar multiplication and addition. So by using the additive and scalar multiple properties of being a linear map a lot of times, we can rewrite this as a1 times t of k1 plus a2 times t of k2 all the way up to an t of kn plus b1 t of v1 all the way up to bm t of vm. Okay, but then look at those things, t of k1 up to t of kn. The k's were a basis of the kernel of t. In particular, they're elements in the kernel, so t of them is just the 0 vector in w. So this whole thing is equal to the 0 vector in w as each t of ki is equal to the 0 vector in w, because ki is an element of the kernel of t. Alright, so what we have is just the same as b1 t of v1 plus b2 t of v2 up to bm t of vm, and that is visibly an element of the span of t of v1 up to t of vm. We have proved that every element of the image of t can be written as a linear combination of t of v1 up to t of vm, and therefore that t of v1 up to t of vm is a spanning set for the image of t. To complete our proof that it's a basis, we must now show that it is linearly independent. So let's go and do this. So we will take a linear combination of the vectors t of v1 up to t of vm, which is equal to the 0 vector. And what we have to do to prove linear independence is to prove that all of the scalars in that linear combination, so all of the ai's, are actually equal to 0. Again, we're going to start by using the linearity property. And we're going to use both linearity properties a lot of times, because t of v1 is the same, a1 times t of v1 is the same as t of a1 times v1, and so on. And we can then, once we've moved all the scalars inside the function t into the argument of the function t, we can also use the fact that t respects vector addition lots of times. And what we will get is that t of a1 v1 plus up to t of am vm is equal to the 0 vector in w. So that's simply using the two properties in the definition of linearity a lot of times. So what we now see is that the linear combination a1 v1 plus a2 v2 all the way up to am vm is an element of the kernel of t. I know a basis for the kernel of t, namely k1 up to kn. any element of the kernel can be written as a linear combination of that basis. But the collection of vectors k1 up to kn followed by v1 up to vm was a basis for v and is therefore linearly independent. If it's linearly independent, then all of the scalars in this linear combination must be 0. Alright, well, forget about the b's. We've shown that all of the a's must be equal to 0. And that proves that t of v1 up to t of vm is linearly independent. We have proved it's a spanning set for the image of t. We've proved that it's linearly independent. Therefore, it's a basis for the image of t, and therefore, as we saw in the last slide, the rank-nullity theorem is true.